So let us come back and do the 2013 paper. That is your part A of your 2013. Let us read this question. This is a bit different compared to other question papers, but let us see this how to solve this question. Although phenoxide ion has more number of resonating structures than carboxylate ion. Okay, we very well know number of resonating structures, that is more highly stable. Okay, right. Carboxylic acid is a stronger acid than phenol. Why? Okay, that is what I have to prove. So as soon as that question is given to you, try to take two important things. What? You have to show the formation of phenoxide ion and carboxylate ion. So let us see. So what is this phenoxide ion? I'm going to take a phenol, and when this dissociates, it forms a phenoxide ion. This is your phenoxide ion, right? Right, and your H plus. Okay, now let us prepare an carboxylate ion, RCOH. Right, when you dissolve, right, in your water, it dissociates into RCO minus plus H plus. Now this is your carboxylate ion or carboxylate ion. Now what do they want us to prove? Carboxylic acid is stronger acid. Now when I see this particular structure of phenoxide ion, we very well know in phenoxide the negative charge, yeah, here the negative charge is delocalized inside the ring. You know, it shows resonance. This shifts, again this shifts, again this bond shifts here at ortho, para and ortho, right? So the whole of the negative charge, what happened? It's delocalized inside this particular benzene ring, right? Here what happened when I write the structure, your negative charge is delocalized between two oxygen atoms. How is this, right? We very well know this shows a resonating structures. The double bond becomes shifts here and this becomes single bond. So how is that structure? This minus the negative charge is delocalized between two oxygen atoms. Now, so what are we saying here? In phenoxide, the negative charge is delocalized. Where is it delocalized? There is a carbon atom here, isn't it? Delocalized around less electronegative carbon atom. Okay, this is a simple thing. Now carboxylate ion. Here the negative charge is delocalized to around two oxygen atoms, right? Very highly electronegative. Oxygen is highly electronegative than carbon. So the drag in the molecule starts. When there is a drag in the molecule, it can easily release that H plus. If it is easily releasing H plus, isn't it more acidic than phenol? So write down negative charge is dispersed around two highly electronegative oxygen atoms, right? When it is dispersed between two electronegative oxygen atoms, what will happen? High polarity or polarity, and hence can donate H plus, thus hence it is acidic. Hence it is acidic. That's it. It is acidic. I can easily have written this. I have already shown this and taught also in one of the reasoning questions. So you're concentrating more on the charge distribution on this. You can also speak in terms of your conjugate base. I already said if the conjugate base, right, or when this is dissolved in water, the ion or the conjugate base, the corresponding acid is a highly acidic acid. This is what also I also said this. If the conjugate base shows resonance, point number one, the corresponding acid, which is a weak acid, when the corresponding acid is the strongest acid, I said, if that particular thing shows resonance. So compared to that concept also, carboxylic acids are stronger acids than phenols. That is done. I have justified. Clearly I have given the answer. So your first part is done. Now let us come back to the next part of 2013. So what does it say? I have to show the following conversions. Conversions are compulsory, chemical distinguishing tests are compulsory, name reactions are also compulsory. Let us start with the B part. How will you bring the following conversion? Propanone to propane. Very easy. Propanone to propane. So write this. What is the formula? Propanone is This is your formula, isn't it? Yeah. Now I have to convert this into propane. This is your propane. Simple. Now we have done one name reaction here. Conversion of propanone to propane. Simple name reaction, that was your Clemmensen reduction. So please watch that. So I'm writing here Clemmensen's reduction. This is a simple basic reaction where I've used a zinc amalgam. Yes, I've used the zinc amalgam, presence of HCl, to convert propanone to propane. So this is the basic simplest conversion which you can use to convert the ketone to your alkenes. Done. Let us do the next one. Benzoyl chloride to benzaldehyde. Okay. Benzoyl chloride to benzaldehyde. Right. So write both the structures. Benzoyl chloride is what? This is your benzoyl chloride. So where did we see this benzoyl chloride? In Rosenman reduction, isn't it? Right. So this is also one way of giving your name reactions. Instead of giving you directly name reactions, they'll give you in the form of conversion. So you can directly do the conversions, right? So this is your benzoyl chloride. I have to convert it into benzaldehyde. Simple. As I said, as soon as you see this benzoyl chloride, you can use a process called Rosenman reductions. Rosenman reduction, you can be used for this. So what should you use? Palladium in the presence of barium sulfate. This is your reducing agent for Rosenman reduction. You can directly convert it to benzaldehyde. This is also done. Simple step conversions, one step conversions. Let us do the last one. I have to convert ethanol to bute to enol. My God, the same question, aldol condensation question. Okay, let us do that again. The third one, I have to convert ethanol to bute to enol. So ethanol, same story again. We are doing aldol condensation. You're going to combine with again the same thing, alpha hydrogen, 1 and H. Yes, this is going to shift here. This hydrogen will come and attack oxygen. So when it attacks in the presence of dilute sodium hydroxide, what will happen? You get COH. We are going to prepare an aldol now, and your CH and CHO. When you further remove water, what did we do? That H is already shifted, isn't it? CH3. So this is CH2. Okay. There is one more H here. Remove this water with this bond. This bond is going to drop in here, and you get. So what is this compound? Let us count. 1, 2, 3, 4. So it is bute. Which bute is this? 2. Which enol? Enol. So I've already got the required product. I prepared this. So let us name this. This is your aldol. Which aldol is this? 1, 2, 3. 3-hydroxy butyraldehyde. Yes. This is your third part. So you can also write here aldol condensation. Right. Let us come back and do the last part of 2013. Yes.